Hi, good morning, everybody. So my name is Dabargha Mukherjee. I think you did a pretty good job and pronouncing my name. So I'm going to give a talk on the past, present, and future of AV1. But before that, let me first thank the organizers of the conference, Virginia, and other folks in Agora who invited me to give this talk. And I'm really excited to be here. Okay, so I don't know if all of you know that AV1 is a latest royalty-free codec that has just been released like about a year or so ago. And this is today the most advanced video codec available. And it may not be the case next year, but as of now, it's the most advanced video codec available today. And it's from the royalty-free domain. So I'm going to give a kind of historic perspective of how this thing evolved. So about 10 years or so ago, Google started this royalty-free endeavor to actually kind of disrupt the video codec landscape. And over the last 10 years, we have done quite a few things which actually ended up made the industry ended up today with what we are here now. So I'm going to talk about the WebM project, which started in 2010. It led to VP8, VP9, and VP10, which morphed into AV1. And then I'm going to talk about what's going to come next. Okay, so let's start with a slide from Cisco's projection for 2021. And as you can see here, it says that by the year 2021, 82% of all internet traffic will be video. Okay, and therefore to cope with this explosion in the video bandwidth requirements on the internet, we have to really develop video compression technologies fast and to cope with this really explosion. So 80% of all internet bandwidth is a really big deal. Okay, so. But Google was really early to really realize what's going on in this video codec landscape. So Google acquired YouTube in 2007 and integrated them over the next 2 years. And then we realized that in around 2010 that we actually needed to have a much better control over the video codec landscape, because so far video codecs have typically been controlled by MPEG. And MPEG codecs, even though they're good and pretty well designed, they are not royalty free. And to really make like even small app providers or app developers really integrate video and really deliver video really easily, and you really need a royalty-free solution for that. And also just to see that around 2010 the video codec explosion was just ramping up, but if you really see what's going on, it was really obvious that you really needed a much faster pace of innovation, because the bandwidth costs were really the biggest costs in providing a really good video experience for different kinds of devices. So traditionally, video codecs have followed this 10-year refresh cycle. So you have a codec like MPEG-2, which was released in 1993, then H.264, which came in about 10 years later in 2003. And so within these 10 years, a lot of things happen. First of all, there is a software deployment. Then there is a hardware deployment when hardware becomes available for decoding first, usually in 1 or 2 years after the standard is done. And then encoding hardware becomes available maybe 2 years later than that. And then these hardware companies that have actually invested in those devices or those chipsets need to actually have enough time to sell those and make money. So this 10-year cycle was regarded as kind of really the minimum that you need. But Google thought that that's actually not really required, because you can actually gain a lot by software-based decoding. So if you made a video codec advancement today, you could deploy it tomorrow in, let's say, if you're in YouTube and Chrome, and that will immediately you'll be able to reap the benefits of reduced bandwidth reduction. And hardware codecs can catch up. So when we started the WebM project, Google's goal was to reduce this latency between codecs from 10 years to about 5 years. So before starting the WebM project, Google acquired a company called Onto Technologies, and they had pretty good codec technologies before that. There was a codec that they had before being acquired by Google called VP8. So after the acquisition of Onto Technologies, Google decided to actually open source that codec, and that became the first royalty-free codec from the WebM project. So it's kind of similar in coding efficiency to H.264. A lot of tests show that they're actually a little bit better, but if you think of the timeline, it's about 7 years too late. So, and by the time VP8 came, H.264 was already pretty entrenched in the marketplace. VP8 is still used in WebRTC as a default codec in YouTube and Hangouts and Duo for devices that cannot support VP9 or AV1. Now, in around the end of 2011, what we started doing was building the next generation codec VP9, and that was built pretty much in YouTube. Although it's an open source project, it was built pretty much by Google engineers. So between this roughly 1.5 year time period, between October of 2011 through July of 2013, we built this VP9 codec. Now, it's kind of important to remember what was actually happening around in that time in the video codec space. That was also the time when HEVC was being developed. HEVC was H.265 is the latest video codec standard from MPEG. So that was being developed around that time, and in each of the meetings, like MPEG usually have meetings every 3 months. So each of those meetings, there were like thousands of submissions. And those thousands of submissions were pretty much from different proposals, making an existing proposal better, optimizing different things. So if you think about it, there's the entire, the brain power of the entire signal processing community in the video codec area were actually focused on building this HEVC codec. On the other hand, in Google, there were like 7 to 8 engineers that were working on building VP9 and trying to compete with HEVC in terms of coding efficiency. But in the end, we were able to release VP9 in July 2013, which is just a little bit after HEVC was finalized. And we showed initial results showing that it's in terms of coding efficiency, it was about similar to HEVC, maybe within 5% or maybe a little lower. And the big bonus is it was royalty free. Okay, so initially there was not, people didn't pay too much attention to VP9. There have been other royalty free efforts in the past, but most of them kind of fizzled, and VP9 was thought of as one of them. There were some initial reports that people tested VP9 versus HEVC, and VP9 turned out to be really bad. And later we realized that it was because when they tested with parameters that were not really the right parameters to use. But internally we started working with YouTube to actually make the case that VP9 is actually in fact about 30 to 40% more compact than H.264 that YouTube was using before that. And at the end, we were able to convince, and YouTube started streaming VP9. So today there are billions of views of VP9 videos every day on YouTube, and VP9 kind of lives alongside H.264 as the format of choice, but VP9 is the higher priority one. So if a device can play back VP9 either through hardware or software, it would receive a VP9 bit stream. If it doesn't, only then it falls back to H.264. And even today, YouTube continues to expand the set of devices and set of use cases where VP9 is delivered. And for real-time communication, VP9 is being used for WebRTC, Hangouts, and Duo in a big way. And external adoption of VP9 outside of Google and Google ecosystems are also catching up. For instance, and Netflix announced Studio VOD, Facebook announced a hardware-based encoding project involving VP9, and Twitch recently announced an FPGA-based live encoding solution with NG codec offering. Okay, so remember when I mentioned that we wanted to have this 5-year codec refresh cycle. So VP8 was in 2010, but that was not really developed within Google or within the royalty-free ecosystem. And then 2013 was the VP9 video codec, which was designed in an open source royalty-free manner. But then if you keep the 5 years, then 2018 would be the time when you release our next codec. So initially we thought that we'd release this VP10 codec in 2010, and we started working towards that as early as 2014, late 2014, and within about a year or so we had about 15 to 20% gain that was achieved over VP9. However, something else happened at the time. So it was because of the success of VP9 through YouTube, it turned out that many other companies started seeing the benefit of royalty-free solutions and going away from these MPEG closed royalty-bearing solutions. And we were able to forge enough interest in that in the community as a whole among other companies to create this alliance of open media. So when the Alliance for Open Media was formed in 2015 or early 2016, the AV1 was decided to be the first codec from that alliance, and we decided to shelve VP10 effort and instead take the tools from VP10 and propose it formally to the AV1 standardization process. So yeah, just to reiterate, the momentum built towards an industry consortium for royalty-free codecs. Many other companies began to see eye to eye with Google after the success of VP9, and the fact that when you actually see VP9 videos on YouTube, they actually looked much better than H.264, which kind of dispelled a lot of the myth that VP9 is actually worse than H.264 that many of the other reports had shown. And the HEVC patent landscape didn't help either, because it was and it still is a mess, and people didn't feel too confident about investing in HEVC. So many other royalty-free efforts also sprung up around that same time. There was a Thor effort from Cisco, a DALA effort from Mozilla, but in the end we decided to join forces together and create this Alliance for Open Media, where we could pull in all our coding tools and create a new codec. Okay, so the Alliance for Open Media, it's an industry consortium with the explicit purpose to build royalty-free codecs, not just for audio, video, images, and also to promote a royalty-free ecosystem around it. So here the current membership of the Alliance. The top 13 members are called founding members, so they have some special voting rights in the board, and then there are additional 29 promoter members. And you can see pretty much all the major video service providers are in this list. We have main additions in the recent last 2-3 months have been Alibaba, Aichi, and Samsung, which are really big names in this space. So if you look at all the Alliance of Open Media members, and they kind of own the world's leading video streaming and real-time communication services, and because royalty freeness is a big part of this of the whole endeavor, you can see that overall the patent landscape is actually quite strong if you combine all the patent portfolios of all these companies together. So we feel that we are kind of safe from being litigated by other companies or patent trolls. So AV1 was the first video codec that was designed from the Alliance for Open Media. The goal was to achieve about 30% bitrate reduction, and the starting point naturally was VP9. It was actually VP9 plus with VP9 with some additional changes, and that was decided as the starting point, and the goal was to at least get close to 30% of bandwidth reduction over that. So it was finally finalized in June 2018, so we kind of lived up to our promise of this 5-year codec cycle. One thing that I wanted to mention that is really critical in this thing is this section here. So there is a patent review process and legal defense fund. So unlike MPEG processes where coding tools are evaluated based pretty much on their technical merit only, and then the patent process happens later, and then they are not necessarily free. Here, because we wanted to make the entire codec royalty free, there's a patent review process is part of the development. So every tool had to go through this additional review to make sure that it's actually safe from being encroaching on other prior art. Okay, and then all the members have to chip in a certain share to create a legal defense fund. So if you have legal defense fund, then whenever any of the players, if any of these members are litigated or sued, they can actually, this entire legal defense fund could be used to fight against that. So this is how the standardization process works. There is a codec working group which does the same thing as most other standards do. They evaluate a codec based on technical merit only, how much coding efficiency it has, how much complexity, and so on. There is a hardware working group that decides to see if the implementation is hardware feasible or not. There is a QA and testing group that conducted time to time perceptual tests on some tools that actually claim to do better in perceptual aspects than PSNR and other standard metrics. But at the end, there is this TAPUS group, which basically says reviews the tool for exposure to patent liabilities. And then only certain tools, only tools that actually made it through that process were actually adopted in the standard. It turned out in the end that, and this is what we had always thought, that most of the core coding tools actually sailed through without any difficulty, because if you looked, there are patents in this space from other companies, but if you really dug deeper and if you looked at the prior art, you can almost always invalidate those patents, because there is almost a lot of prior art that are very similar that you can bring to bear. So only things that we had problems with is really high level syntax bits. For instance, whether you want to send a bit to indicate whether you want to filter across style boundaries or not. So things like that were more problematic, but in terms of the core coding tools, most of them actually sailed through really well. So I'll spend a few slides on the coding tools, but not too much in detail. The AV1, the coding framework is pretty much the same as most standard video codecs. You code frame by frame, and every frame you encode, you have a set of frames that are available to you from the reference buffer, a reference buffer stored, and you can choose to encode them using one or more of those frames, or you can also use them, encode them using interprediction, which means you can predict them and code them using the pixels on the top and left of the current block. There is an elaborate partition mechanism. So within every frame, you would break it up into a super block, which may be of size 128 by 128, and then you would hierarchically break it down into smaller prediction units. In terms of the coding tools, we have several interprediction modes. The two that I wanted to highlight a little bit are kind of the ones that are new and different from other standards that have existed in this space. So one is a recursive interfilter, which basically uses some kind of a data driven mechanism to decide the weights that you would use to predict every pixel for every 4x2 block, given that you know the pixels in the surrounding area. Okay, and then there is also another tool called Chroma from Luma, which is quite different and very useful. And what it does is it actually predicts or reconstructs the Luma coefficients first, or the Luma pixel values first, and then using the high frequency component of the Luma prediction, it actually scales that by a certain amount that is indicated in the bit stream to obtain the predictor for the Chroma coefficients. And in that way, it gives you get a pretty good prediction for the Chroma components. In terms of the interprediction tools, interpredictions are the prediction tools that are that you predict a block using other reference frames that have been already encoded. We have actually explored a lot in the space of compound prediction modes. So compound prediction modes are those where you combine two predictors in a certain way to create a final predictor. So for instance, there is this wedge prediction modes, which will tell you that whatever you see as black here are going to be predicted from one of the predictors, and whatever you see as white is going to be predicted from another predictor, and then you combine them with a weighting scheme. And then if you see this thing here, the black and white basically are weights, but there is a gray zone in between. So there is a smooth transition from one predictor to the next. There is a similar one that combines inter and intra predictors together, which is also pretty new in video codecs. Then this is also the first standardized video codec where we introduced affine motion. Like traditionally all video codecs so far that have been standardized have used only translational motion models, because it has been pretty hard to extract any benefit from more complex models. But AV1, we have been able to extract benefits through two tools. One is a global affine warp mode, and then there is a local affine warp mode. So both of them actually show substantial benefits over using just purely translational models. And then there is overlap block motion compensation mode, which has been, this is not entirely new, but it has been, it kind of was used in H.263 in the 90s, but then it fell out of favor. But then we brought it back here in AV1 because we could get a lot of benefit out of that. In terms of the transforms that are used for coding the prediction residues, we have up to 16 different transform types that are used. Traditionally, video codecs have used only one, like DCT. HEVC uses DCT and DST. VP9 also uses VP9 and DCT and DST. But in AV1, we have expanded this a lot more to actually be a much more comprehensive solution. So we have 16 different transforms, and the 16 transforms are basically a combination of 4 possible transforms horizontally and 4 possible transforms vertically, and the 4 possible transforms are DCT, a DST, a flipped version of DST, and an identity transform. And also within a prediction unit, you could recursively break it down into smaller transform units, and each transform unit could use one of these up to 16 transform blocks. One area where VP9 really or AV1 really pushes the envelope in the video codec technology is this in-loop filtering. So traditionally in video codecs there is an in-loop filter. HEVC has a filter called SAO or sample adaptive offset, which is also an in-loop filter, but in AV1 kind of really pushes the envelope in that and actually allows you to have a lot more flexibility in how you may want to use this in-loop filtering. So after the deblocking, we have a filter called CDEF or Constrained Directional Enhancement Filter, which is really a edge preserving smoothing filter, and which works really well, especially for real-time communication applications when you don't have the juice to actually use other tools that are more complex. There is an upscaling operation that can be done. The upscaling operation is, I'm going to explain this a little bit more. There is a loop restoration tool which comes after the upscaling operation, and that's a combination of 2 additional tools. One is a Wiener filter and another one is a self-guided filter. Now in combination with upscaling, the upscaling and loop restoration together has this the ability to do super resolution. So and this is the first video codec which allows in-loop super resolution. So what you can do in the AV1 bitstream, and this is will be supported in hardware and supported in all compliant decoders. Like you can start with a frame, reduce the resolution to a certain level, then you can encode it and then go do the deblocking and the CDEF filtering at the low resolution domain. Then you can upscale with a normative upscaler, and then you use this loop restoration filter. The loop restoration filter is a learned filter which has this ability to or get back some of the high frequencies that you have lost in the reconstruction process. So a compliant decoder will need to support this anyway. So the encoder has a lot of flexibility to actually choose as it's encoding when it's going to go down to suddenly to a lower resolution. Suppose in a real-time communication application you suddenly have a bandwidth bottleneck, you may go down to a lower resolution and you can go back up, and you have a lot of flexibility in making good encoder decisions. So we are really starting to scratch the surface here on how we are going to make good encoder decisions, but it's really good powerful feature to have, especially for real-time communication applications. Okay, now in coding results, so this is it's always been controversial, but this is the coding results that we get from an rvcompressedstate.com, and this is the official test infrastructure for AV1. So this website is actually free and open. Everybody can go in and see how the test, what the test conditions were and how the tests were done. But so this particular table shows BD rate. So if most of you probably know, but BD rate refers to the amount of bit rate reduction or increase you have over a baseline. So any number that you see here that is negative basically means that it's like it's over a baseline, it gives you that much reduction, let's say 25.97% reduction in bit rate at the same quality. So here this table has VP9 as the baseline, and then we compared X.265, and then we compared AV1, the libOM AV1 encoder at different speed settings. So AV1 libOM is the main reference software as well as the production software for AV1 currently. So it has several speed settings. CPU 0 means it's the slowest setting which gives you the best quality, and you can go up to like higher settings as you like, and each step probably will reduce the encoding complexity by a factor of 2 or 3. Okay, so if you see here, of course the CPU 0 is the slowest setting of that. You get like about 28% reduction in bandwidth without losing quality as compared to VP9. And if you compare it X.265, you can see X.265 versus VP9 is roughly neutral, so it's roughly similar to HEVC. The VP9 is roughly similar to HEVC. And in terms of the Chroma components, actually it turns out that it's actually a lot better. And that's probably because X.265 actually is not very good for coding Chroma, but AV1 is a lot better. So once we there are some test results that were conducted by third parties. Facebook, for instance, they also did a test of AV1, and they saw that AV1 handily beats X.265 and VP9. MSU did a video codec comparison. This is their final slides from last year, and then they showed that compared to X.265, VP9 is about 25 to 30% more compact, which is exactly the same as what we got. Bitmovin did another experiment. They saw that AV1 is about 40% more compact than HEVC also. Okay. Now, one of the things that we have been asked to do, like when you present these results, I think from the MPEG community, we have been said that don't compare against X.265 because it's not the best in terms of coding efficiency. Instead, you should compare against the HM. So, and the claim that we heard that HM is about 20% better than X.265. So we did our own tests, and it turned out that HM was not actually 20% better than X.265, but it was better by about 5 to 6%. So if we compared against the HM, so the RE compressed yet, which is the public open site, is not really available. It doesn't support HM, but we did our own internal tests, and we saw these results. Like in terms of average PSNR at the higher resolutions, we get up to 25%. In terms of SSIM, it's actually a little bit more than that, but it's still about the same ballpark as 25% better than HEVC. Now, we are about to release a comprehensive study comparing AV1 LibOM encoder with the HM very soon. So stay tuned for that. So, and we commissioned a third-party company to run those tests independently. Okay, in terms of the coding speed. So in terms of encoding speed, it turns out that the gain that AV1 gets, about 25% better than HEVC, doesn't come without any cost. It does have an encoding complexity cost because you are pretty much vastly expanding the encoding search space. So you have this several speed features or speed levels that I mentioned, speed presets. So this is how the speed comparison today is compared to VP9 at the slowest speed setting. So if you compare, let's say AV1 speed 0, which is the slowest of AV1 versus HM versus VP9, it will be about 15x more complex. However, if you go down to speed 0, it's currently less than 2x, about 2x the computation time. But this is something we are working on actively in the LibOM encoder. So every day we are getting better and better speed ups without losing quality. Okay, and this at the CPU is 4. It's about 2x the encoding time of VP9, but it's still about 20% more compact. Okay, so in terms of adoption for AV1 so far, so already AV1 is being served by YouTube for 360p, 480p, and 720p content for the most popular, and with 720p is just ramping up. In terms of apps, everything is being decoded in software right now because hardware is still not available. We expect hardware to be available in 2020. So as of now, all that is browsers like Chrome, Firefox, Edge, and VLC support VP9 AV1 decoding over Windows, Chrome OS, and Linux. And but we are still in the early stages. When the hardware ramps up, becomes available next year, we're going to see a huge increase. In terms of the future, this is what we expect. Like in 2020, we will expect TVs and mobile hardware decoding to be available, and mass market mobile and desktop laptop decoding will be available maybe in 2021, and everyone will penetrate lower end devices hopefully by around the 2022 time frame. Now advances, so far all the work that has been done in AV1 is on the LibOM code base, but advances beyond LibOM from outside Google is actually quite important. So there is a decoder for AV1 now, which is called David, which is really good. And so many browsers are actually using David for decoding now instead of LibOM. And when the encoding efforts are also ramping up, there is an effort from Intel and being supported by Netflix that is called SVT AV1, which is really a fast encoder, but in terms of encoding quality, it's still a lot behind LibOM, but hopefully it will catch up in a few months. In terms of looking at the future, so AV1 is definitely not going to be not going to remain the most advanced codec maybe next year when VVC comes out. All our projections say that VVC will probably maybe 5 to 10% better than AV1, even though it will be much lower, much higher decoding complexity wise. However, the advancements in video codec technology do need to continue, so that's why we need to keep pushing towards AV2. And if we still want to keep with this 5-year time frame for codec refresh, AV2 should be due in 2023 time frame. Okay, but does it make sense to actually have AV2 in if it doesn't achieve 25 to 30% gain over AV1? We don't know. There is a huge technical risk, but we are going to explore all the different techniques that we know of to actually to make that possible. So one of the things that we definitely need to explore is machine learning based technologies. I think some of them are promising, but we also don't want to be too ideologically driven by machine learning and say that only we don't need anything else and just use machine learning and it will solve everything, because it won't, because almost always you're going to over provision resources if you're going to use machine learning only. In terms of real-time communication, there is a problem that we see. So far in the last 10 years, like there have been 3 codecs that have evolved, 3 really advanced codecs and 1 more coming out next year. So 4 good codecs have evolved in the last 10 years. Like between 2012 to 2020, there is HEVC, VP9, AV1, and then 2020 will have VVC. So all of these codecs are really good in the VOD space, but if you look at the real-time applications, the constraints are very different. And if you have very different constraints, after the codec standard is done, you have to put in a lot of engineering hours and resources to actually optimize the codec to satisfy the real-time encoding constraints. And in the end, you may end up with a set of tools that are really not optimal for the real-time use case. So one food for thought I want to leave everybody with is the fact that maybe for the next codec, maybe it's better to actually have explicitly a codec that is for real-time communication applications. And so that means that entire testing and infrastructure has to change so that we don't just test the low delay and random access mode without looking at the encoding complexity, but the encoding complexity also becomes part of the evaluation process. So yeah, and if we did that, I'm pretty sure that the codec that we would land up today for AV1 or VVC or even HEVC would be very different from what they are today. So ideally what we may want to have is one codec instead of having 2 codecs, one for real-time applications and one for VOD. You just have one codec, and there will be some tools that are common to VOD and RTC applications, but some tools are only applicable for VOD and some tools are only applicable for real-time applications. So if we can create a codec or a bit stream that has these properties and also change the standardization process so that the real-time part actually is evaluated the right way. These are not easy tasks, but then I think it will, this 1 to 2 generation, the fact that real-time communication codecs are actually 1 to 2 generations behind will no longer be the case. Okay, so that's all I had to say. And thank you.